Hi, good afternoon. Hope everybody enjoyed lunch. And hope everybody's still awake after lunch. So, Luther Birdzell, I'm the founder and CEO of OAG Analytics. We're based here in Houston. I founded the business in 2013 after exiting a business to Computer Associates. My background is in electrical engineering and software. So in 2013, I was brand new to the oil and gas industry. Very quickly, this problem of how do we estimate the production of an oil well before it's drilled came into focus for me and has been, well, nothing short of an obsession since. When we started this journey in 2013, one of the first things that we did was use machine learning with geogrids, with historical completion data, and historical production data, and we're able to automate essentially a type curve. We didn't have super granular, well-specific insights, and we definitely did not understand concepts like depletion and interference, and specifically how those two physical concepts impacted the production of wells, especially with tighter spacing. Something I want to point out here as we kind of get into this, why is well spacing an important problem? Well, if for no other reason, Wall Street, that provides the capital that we need as an industry to extract hydrocarbons from the ground, they think it's an important problem. And we've seen, kind of historically over the past 12 months, stock prices, especially of the 20 largest US independents, tended to follow the WTI. And if we look at the graph on the left, we see something really different started happening in July, approximately July, August of this year. WTI hasn't been quite as volatile. It's kind of been in that $55 band. But we've seen in the stock prices on the right this precipitous fall off across the industry in equity values. And the aggregate of that, it's over $10 billion in equity value has been lost since July of this year. And it's not an effect of the WTI, it's something else. I think well spacing has something to do with it. So fundamentally, why is this such a hard problem? Well, first of all, the well production is this really complex, high-order, nonlinear function of the rocks, of the well design, of the distance between the wells, and of the time offset between when the wells are drilled. Distance between these wells alone does not effectively describe this phenomenon. And similarly, the kind of binary, well, we have a parent, that's a well that was drilled first, or a well that was drilled that wasn't affected by the depletion of other wells. And then we have children that come in later or infilled that do. And what we found is that binary classification isn't quite enough either. So to really get this, we've got to combine traditional physics, reservoir physics, with machine learning. And what we found is it's really easy to say. I mean, you go to any website, Google it, it's everywhere. The reality is really hard to do. So if we look at a quick retrospective history here, as an industry, when we moved from paper to digital in the 90s, we had tools like Lotus 123, later Excel, and we were able to learn more from the same data that we already had. About a decade or so later, next major breakthrough that's been adopted at tremendous scale by the industry, tools like TIBCO Spotfire. Again, do higher order analysis, interactive visualizations, and we were able to learn new ways to reduce D&C costs and increase our EURs using the same data. Well, AI and machine learning, combined with cloud, properly connected into that technology ecosystem, is the next inflection point that's enabling us to learn substantially more from this same data that we already have. So a little bit about how we've integrated AWS, especially SageMaker, with TIBCO Spotfire. So first thing, it's always everybody's first question, what's the data? It's a critical question, no matter how fancy the acronyms get around analytics. Garbage in, garbage out, does not appear that it's going to change anytime soon. So we've got to have good data. The most learning usually comes from combining public data from sources like Drilling Info, IHS, and others, with the proprietary data that's stored in systems like WellView, production data in Aries, subsurface data in systems like geographics, Petrel, Petra, and then of course connecting to just general databases that can house all kinds of other information. So the first thing that we did when we started this, there's all these, everybody talks about the silos between all this data, and no joke, I mean, in very sophisticated, incredibly capable oil companies, we've seen it take 3 months to bring together to create a single data set from just those simple data sources. It shouldn't be that way. It doesn't have to be that way. One of the first things that we do when we work with companies is help really speed that process up, and more importantly, make it evergreen by using automation. Data scientists, software people, we call those data pipelines, and specifically automated data pipelines. But essentially what we're doing is connecting to all of the current systems and putting an automated process in place to bring that data in a normalized, standard way so that it can all be combined together in seconds, and populating a master database in the cloud. Specific Amazon technologies we're using there, you can see RDS, S3, and EFS are part of the collection of over 17 AWS services that are part of this aggregate solution today. And then we use SageMaker, primarily it's Python code written by data scientists and software engineers that runs in SageMaker. We have unlimited storage, unlimited compute, and Amazon has just done a masterful job of making that really, really easy. Kind of on the other side of this, we have our standard workflows today. And Spotfire, in most of the industry, most of the US unconventional focused industry, especially among those larger independents in the Permian, Spotfire is just an instrumental part of all these workflows. It was the first partnership that we built as a company all the way back in 2014. Michael O'Connell, who's now the Chief Analytics Officer, had a different role, different title back then, was incredibly supportive and has continued to be a great ally. So again, using the same kind of RESTful web services and APIs that we use to integrate to Amazon, we also integrated to Spotfire. So we were able to connect this unlimited data storage, unlimited compute in a virtually seamless way with the industry standard data visualization package. And I'm going to show you what that looks like in a minute. So more importantly though, technology for technology's sake. I'm a technologist, born engineer. That would do it for me this afternoon, but that's not what you all here are for. You all are here to, my understanding anyway, is learn more about how we can use that enabling technology to improve and create some real value for the oil and gas industry. So specifically, we're going to look at a case study of planning drilling units, going to look at some aspects of infill, as well as planning new drilling units. There are some nuances that are different, but fundamentally they're very similar. So the big question here, we put well A in. That's that parent well. We drilled that in October 2018. This, by the way, is a hypothetical use case. These are not real wells. Very, very sensitive. Industry is very sensitive about customer data. So parent well goes in. 6 months later, 9 months later rather, we drill parent well B. And today we want to come in and drill this other well between these. So wells A and B were more than 2,000 feet apart. They didn't interfere with each other. They weren't depleting from the same reservoir, particularly through the first couple years of their production. The depletion area of a well grows over time. When we're putting another well in, there's also the overlap of those two wells, because not all these wells go in exactly parallel to each other. So as a function of that, we'll call it percentage overlap on a volumetric basis, and then as a function over time with an expanding depleted area, it's a pretty tricky equation to figure out as a function of the specific rock properties here, the specific completion design and how those are going to interact, and then this complex geometric function that changes over time about how much these wells are going to essentially share the same milkshake. This is a tricky problem. But essentially here, what well C is going to come in with substantially less production than wells A and B, and we're going to use machine learning and physics together to come up with really accurate estimates for when that happens. So this is our case study. A couple of things we do on the path to this. Top left-hand corner, we have a plot that I'm sure every reservoir engineer in the room is familiar with and probably hates as much as I do. And this is just looking at any of these raw system drivers: fluid, proppant, lateral length, stage spacing, cluster spacing, so on and so forth. And if we look at any of those dominant system drivers relative to production using a simple two-dimensional analysis, we always see the same thing. There's no correlation. It doesn't mean there's no effect. Fluid, of course, has an effect on production. But all this data in the unconventional reservoirs is so autocorrelated, right? Everything relates to everything else, and you just can't unpack that in 2 dimensions. So one of the first things we do using advanced analytics is essentially filter the noise out of these signals so we can better isolate the impacts of the individual system drivers. The better we can understand the building blocks, the foundation, the more risk we can mitigate. Then below that, with that foundation of improved data, we're able to train machine learning, again, combined with physics, that for one very specific, either 1 square mile or 2 square mile area, right, our drilling units, whether we're doing 640s or 1280s, we can get a very strong trend about the effect of well spacing on production and ultimately economics in that one specific area. In our use case here, 700 to 800 foot spacing. And by the way, those little black lines are 95% confidence intervals. So planning new drilling units, then we're going to go in a demo and take a look at this. What we're really looking for here is, do I drill 8 wells or 10 wells? And which completion designs should I consider? The drilling unit, I guess we'll give you the answer before I look at the demo. The specific drilling unit we're going to look at here in the demo, 8 wells, produces better NPV than the 10 wells. Several sections over, just a few miles to the east and a few miles to the west, we see an invert, and you can actually get better economics in that rock from 10 wells. So there's some very localized effects here that require some very precise, benefit from higher precision. So I'm going to take a look at the demo now. Give everyone a minute to read this. Hopefully hopefully there's not too much new information on this one. Okay, so this is the data science workflow. This is the web-based interface that is running in Amazon EC2. We're doing a Bakken example, good quality public data. We have our workflow templates. This is that data library. We populate, and here we're very careful just to use public data. When we set this up for customers, it's all of that proprietary data from your systems like WellView, Aries, PhD Win, Geographics, Petra, Petrel, and so on. Combine that with the public data, and then simply any data set source on the left-hand side that we select the checkbox for is going to be active, and then every column that we choose on the right-hand side are going to be the columns that are included. And instead of it taking 3 months to put together the single data set from that aggregate set of information, literally takes less than 3 minutes here. This is pretty low-hanging fruit. As far as our technology goes, this is some of the least exciting stuff we do, but important to note that there's still a lot of value creation here. It's a really important piece of time savings. You can't go fast with analytics. You can't test the iterations quickly without being able to try different data and different filtering and QC on the data. A lot of different ways to filter data. There's folks who love the rule engines, kind of Spotfire style. We've done extensive user studies and found that this is consistently 12 times faster for QCing data, just using the maps. There's a couple pieces of information then that our system needs to understand to be able to apply our algorithms, and this is the configuration for the physics algorithms. So we need to know what kind of production we're looking at. We need to know the locations and ideally the azimuth of the wells. So we're getting the surface hole and bottom hole, latitude, longitude, or UTM coordinates. And then we need to know the time offset. And if we know the spud date and the completion date, there becomes a lot that we can do. Like those 5 simple pieces of information are the inputs to these incredibly difficult algorithms to write that really unlock the value of machine learning for helping improve well spacing for the oil and gas industry. So here we've configured our analysis that's about to go run in SageMaker. So we click select, or we click go there basically. And this is just a quick preview, hard to demo, Python code running in the back end. We use over 17 Amazon services represented here. Again, that RDS S3 EFS aggregate of our data lake solution running with SageMaker and Kubernetes for elastic deployment. So that's a really, really cool service for those of you guys who aren't familiar with it. It's auto-scaling. So as more users start using it, starts adding more servers and more resources. As workloads back off, it automatically scales back down. It's an incredible use case around the cloud. Well, plenty of people around who can talk about all the other logos up here. Just wanted to make sure we gave that a little highlight before we moved on. We're going to come back now to the data science workflow, and the last piece then is to download these Spotfire workbooks that we automatically generated as part of this machine learning pipeline. So with Spotfire here, we've also built an integration. So you log into the Spotfire server, which most of you I'm sure are probably familiar with. You also log into OAG Analytics using the same credentials that you do for the web and really all of our other connection points that are all using those S3 or Amazon services. So we've now got these simulation results. And what we're looking at in the top left-hand corner is IRR versus CapEx. The top section is 8 wells per is 8 well spacing. The bottom graph is 10 well per section spacing. And we've highlighted the highest performing completions. So this, using a high fidelity tool that's combining physics with machine learning, we looked at basically automated a process that in seconds gave me the results of almost every viable option that a reservoir engineer would consider, both for the 8 well and 10 well scenario. The engineer then says, okay, show me the top decile roughly, the best performing of that set. And that engineer now, a couple weeks ago, that engineer was spending 70 to 90% of her time coming up with one good scenario that she was going to recommend to management. This technology is enabling her to spend more than half of her time today applying the most valuable thing that we as humans have, judgment, to a set of automated, really good options. That creates better outcomes. So we see here then that the average NPV for these wells, again in this specific drilling unit, this specific rock profile, is better with a little bit wider spacing here. Again, slightly different rock profile, and that can completely invert, and it happens within the same townships. So I think there's just another second of this here. So 8 wells, better performance, but we already all knew that answer because I shared it before we started. So the 1 or 2 pieces here and more pieces, and I want to open this up for Q&A. All right, first time I've tried to do one of these demos in this exact format. So this will just run 1 more second, should be done, and then we're ready for the next slide. So on this slide, we're looking at parent wells A and B and some specific results. Again, this is representative of work that we've done for multiple customers over 3 million acres throughout North America. The type curve, the yellow, is different from machine learning. The type curve's job is basically a reservoir engineer is going to look at the wells that are similar and nearby to this one we're drilling. And then if we have enough of those, we take the average of them, and we get a really good estimate about average production. And it's usually about 3 townships, which translates into about 100 square miles. A lot of those areas have a lot of these wells that were not affected by each other. So the average is, representing kind of wells A and B, the parent wells. In theory, if we had really densely infilled areas, the average production of all those same type of wells would be closer to the children, those depleted children. Same well design, right? Same cost, but produces much less oil. Reality is most type curves are doing a really good job today of estimating wells by themselves. They're not doing a really good job of accurately estimating the offset production degradation of those children that are infilled later. Machine learning, mentioned, it's where our journey started. There's a handful of companies kind of like us today who are using machine learning to automate type curves. It's a great time savings. It's got a nice tactical value proposition for most operators. But machine learning alone does not understand enough about physics to capture the depletion and interference concepts that allow us to really accurately estimate the degraded effects of the offset production on these children. When combining physics with machine learning, it's possible to do it. And we haven't done it with physics. Physics alone has not been successful yet. Machine learning alone has not been successful either. And I think machine learning alone not being successful has left a lot of people really underwhelmed, especially in this industry, because there are other industries that, quite frankly, the cost of the data is cheaper. They have a lot more data. And in theory, if you have enough high-quality data, you can learn that whole system, or machine learning can learn that entire system from the data alone. Our data is too expensive. I mean, there's nobody here who's 2 years old in the room, but like in our lifetimes, we're not going to have enough data to estimate that, to solve well spacing using machine learning alone. Have to combine physics. And if we use physics alone, that's an option. We all know what kind of results we get there. Get these log normal production distributions. It's kind of in the standard. There is an opportunity to improve by learning more from the data that we already have. So just one more sec. This is who we are, what we do, and really wanted to thank everyone for the time here. That's what we have for the presentation. I would love to, oops, sorry, can we back up one slide, please? This was the Q&A slide. So I'd love to open this up for any questions. Yeah, please just speak up. Okay. I'll do my best to answer this. Again, I'm the electrical engineer software guy on the team. We have about a half a dozen PhDs in subsurface and reservoir engineers and all. So I don't want to get too out of my depth on the industry reservoir physics. But fundamentally, what we've done is, if we can agree that depletion of a reservoir and the interference between wells, specifically when those frac wings kind of overlap and specifically when frac wings overlap, that those are physics-based phenomenon. Yes? So if we train a machine learning model and do blind, with about 80% of the data we have, and do blind testing on the rest, and we are systematically, we're going to be right most of the time, but there's going to be some areas where we're systematically over-predicting or under-predicting. Those areas where we're systematically over-predicting child well offset production is one of the biggest obstacles to asset teams adopting machine learning in a meaningful way for well planning today. And we've seen a lot of this for 6 years. When we can add algorithms that are PhD geophysicists, petrophysicists, geologists, mathematicians, and software engineers collaborated on, and we apply those algorithms. It's a function. It takes as the input the production data, the surface hole location of the well, the bottom hole location of the well, the spud date, and the date of first production. Those 5 inputs to a function, an algorithm. The output from that are additional columns of data that understand take those kind of input pieces and then output columns of data that have these transformations applied that understand depletion and interference in a way that we then, when we feed that data set into a machine, into SageMaker, the model that we get out no longer has that systematic over-bias of overestimating the child wells, but rather fits them almost perfectly. Machine learning on a standalone basis, it is impossible to prove that we can use this technology to optimize a well without deploying capital. What we can prove, and this takes about 8 weeks, is that we can improve predictability, right? So it's in the past, if we could have, data we had at the time, could have helped us avoid some mistakes, or conversely, if it could have helped identify some opportunities where we could have got even better economics, that's the win. Go ahead.
Incorporating geological data into the training of the model?
Oh, yes.
Okay.
This does not work without geology. So excuse me for not being clear, is a really important point. The geogrids that we export from systems like Geographics, Petra, Petrel are the primary geologic inputs. There are many other things that we do with subsurface data, but simple high level, initial starting point, it's the geogrids. This does not work without that data. Our approach is a hybrid. So, if we want to say, well, if we're starting with the data, and that data from Petra and Petrel, that's primarily physics-based. So we're starting with physics-based insight already applied to the data. Then we apply even more to help that better understand depletion and interference, and then we apply machine learning, and we can get substantially better results than a type curve from that. That's a challenge, and that's why an integrated interface is so important for this. So the data you're looking at, right, what data are we going to use, right? Especially, yeah, absolutely. What data are we going to use? Which columns of data are we going to use from which data sets? And then specifically, which rows of data we're going to use, which is that outlier filtering, that has to be done in the same software. I guess it doesn't theoretically have to, but I can't imagine not doing that in the same software. And we've, at the beginning of our projects, we usually like everybody else, spend 70–80% of the time with the data. Operational teams don't have to be spending that much time with data wrangling. And that's one of those areas that, that user study that we did and really tightly integrating that stuff, we've been able to reduce that cycle time by 12x at many, many companies. So, for example, want to go test some additional hypotheses, right? If we can reconfigure and re-QC that data in minutes instead of days, that's a big win, and that really facilitates the iterative testing, which is critical to the last mile in this. Because it's all the physics, it's all the data science, and then really the last optimization with all this is about just trying a bunch of different things. Okay, well. All right, well, thank you all very much. Good luck with your well spacing. Hope you enjoy the show.